The broadcast is now starting. All attendees are in listen-only mode.
Hello, and welcome to Think Big Analytics webinar on searching billions of product logs in real time. Today we have Ryan Tabora with us. He's Senior Data Engineer at Think Big Analytics. Just some housekeeping items. If you have any questions, please feel free to type them into the GoToWebinar screen there, and we'll answer them at the end. If anyone is particular um, to a specific slide, I can interrupt Ryan if it's urgent. And there will be 2 poll questions throughout the presentation, so if you wouldn't mind taking a minute to answer those, they're very helpful to us. With that said, let me hand it over to Ryan.
All right. Hello, everybody. Like she said, my name is Ryan Tabora, and I am a senior data engineer at Think Big Analytics. Think Big Analytics is a big data consulting firm. So I act not only as a consultant, working with clients to understand requirements to get like business value out of it. I'm also one of the core coders that we have. So I've worked hands-on with these technologies I'm going to talk about: HBase, Solr, Hadoop. Whatever I talk about, I've worked hands-on, I've coded this stuff, so I've got some good experience on that. And then personally, those are my 2 doggies. I love dachshunds, I love bass guitar, and I love zombies. So I'm sure you'll hear some references to those things as I'm going through this talk. All right, so what are we here to talk about? We've got a very flashy title, searching product logs in real time. So I'm going to talk about what that actually means in a concrete sense, give a little background, talk about big data in general, the different technologies that we're using. And then I'm going to go right into a use case. So we've had multiple clients that have had this kind of a similar problem, and we've got kind of a standard solution to these problems. It's not the only solution, absolutely, but it's just one that we found that's worked with a few of our clients. So I'm going to go through that use case, talk about some designs that we've used, and then go through some possible alternatives. And at the end, I'll wrap it up and let you guys ask questions. So let's get right into it. So what are these product logs per se? I like to also call them device data. Essentially, it just refers to if you as a company have a set of devices, whatever they are, whether they're phones or machines, whatever it is, these machines are creating data. And then on some periodic basis, these devices are sending data back home. So if we're talking about like Apple, for example, our iPhones are all creating data, and then once a week they're sucking up the logs on that device. And this could be any kind of information. It could be configuration settings, like how high do I have my brightness set? Or it could be event settings, like I opened and closed Facebook 50 times this past weekend. Or it could be performance, like how long the battery lasted. There's all different kinds of data generated by these devices, and it goes across all kinds of different companies. I mean, anyone can have product data. It can be an energy company. They've got these smart meters that are creating data, and they're sucking that data back. You've got companies like NetApp that have servers, and these servers are creating logs and pushing them back to home base. That's what device data is. So it can really apply to a lot of things. It doesn't necessarily have to be log data. I mean, this data can come back in any kind of format. Could be binary, could be textual, could be a compressed archive, could be anything. The idea is that you've got many, many devices creating data, and they're sending them back to home base. And if you're doing well, you're going to have more and more products, which means more and more data, which will eventually lead to your big data problem. So what kind of cool things can you do with device data? First one is real-time visualization. So for example, I brought up energy companies. They want to know in real time, where are the hot spots? Where, if there's a San Francisco 49ers game going on and there's tons of energy being consumed by that area, we want to route power that way. So real-time visualization of things happening. Real-time response. So if you can be alerted to a device failing, you want to be able to respond to that as quickly as possible. So, like if a customer, a log comes up, hey, my disk drive is broken on my computer, that log is automatically sent back. You can automatically send them a new disk drive before even the customer knows. Then you got things like ad hoc analysis. So this is where like data science comes in and business analytics, where you want to kind of just ask random questions about your data. And I think that one's pretty clear, but there's a lot of power there. And then really what fuels this is two different things. Full historical capture. So you'll find a lot of times these clients that we go to, they can only capture, the past months of data, or maybe even just the last snapshot of data. The real power comes in, for example, if I'm looking at drive failure analysis, I want to say, let me look at the configurations for this device for the past year, and let me see what led up to this failure, so I can maybe predict another failure in another machine later. And then blended data sets. I want to pair up that configuration data with my sales data. What devices are these people buying, and how are they configuring them? There's obviously the power of device data is immense, and really it's up to you what you do with it. But it's going to require a system that can capture a lot of data, and a system that can also analyze that data quickly or in kind of a batch way. And we're going to talk about how you can do that in the next few slides here. But before we get into how we're doing that, let's do a quick first poll to learn a little bit more about the audience here. So I'll hand it off to Anna for that.
So the first poll is
Anna, you might be muted if you're talking.
How would you describe your big data technology experience? And we'll give everybody a minute to answer that. Great, Ryan. It seems like most of the folks on the call are in the intermediate stages of their big data project.
Cool. So maybe some of you guys have worked with Hadoop or worked with some NoSQL technology like HBase or Cassandra, and you guys want to know how to get search in there, which is definitely something we get asked a lot. So let's talk a little bit more. So traditionally, when we go into these clients who have these kind of device data product log problems, we find that they've already tried doing something with some kind of relational database, whether it's MySQL or Microsoft SQL Server, whatever it is. And you could fuel a lot of actual search applications on a SQL product like these databases. You have your joins, you have your regex, you can do things like searching different fields, and that'll satisfy a lot of different search applications. But obviously, the problem is, once you get to a certain amount of data, sharding or whatever it is becomes completely unmanageable and too difficult. So they start looking to other things. I should also mention that there are things like MPPs, like Netezza or whatever it is. These databases can scale, but they still require kind of you to fit your data into a certain model, and it's expensive. So let's talk about some open source options. First, let's talk about storing your data. Obviously, the big one is Hadoop. And most of you said you're intermediate, but I kind of want to go over it at a very high level just so everyone understands. Hadoop is a distributed storage and analytics platform. The storage piece is called HDFS, and that stands for Hadoop File System. And it's essentially a way to store your data across a cluster of nodes. And it scales simply by adding more nodes. So that's kind of the beauty of Hadoop. So, and it's really easy to get your data into Hadoop as well. You don't really have to apply a schema to your data. You can do something as simple as just copy a set of data into Hadoop. Now, there's a few of you out there who are saying, it's not that easy. Sure, there are things like small file problems, etc. that require you to do some manipulation of the data. But really, at the end of the day, if you want to play around with Hadoop, you can install it and just drop data in there, and that's the beauty. There's no schema required, and it can scale very easily. And Hadoop really, it's a file system. It doesn't have the search capabilities, so if I want to find a line of text inside of one of these files, it's not going to be very easy to do that. Those search features aren't built in. And also, Hadoop is meant for kind of streaming access to large files. So you kind of want to sequentially read huge files in Hadoop. The ideal scenario is, you've loaded 10 terabytes of data inside of Hadoop. You're going to do some kind of batch query over that whole 10 terabytes, read the whole thing in, and then do some kind of analysis on it. That's one use case. Another use case that people have often is, I want to just see little pieces of data that is kind of scattered around my 10 terabytes or 10 petabytes of data, whatever it is. And for that, we need a different technology. And generally, we point to NoSQL databases there. So things like HBase, things like Cassandra, things like Cumulo that allow users to kind of do real-time access to small bits of data scattered about your data set. And again, here the search features are limited as well. So with HBase, everything is kind of based around your row key. So you can look up pieces of data by its row key. But that's pretty much it. You can do row key scans, and you can design your row key in a very special way so that it satisfies certain use cases. For example, I could say my row key is going to be customer name, and then next to that it's going to be the date. So in that case, I can do a row key scan on customer A for dates, January to February. So you can get kind of creative there, and you can do kind of search-like things there, but still it's extremely limited to the search applications that we know about, like Google or whatever it is. And Cassandra also has some secondary indexing, so you can query on some of the data inside of the columns, but you're still missing out on a lot of the features like group by and all different kinds of advanced analysis that you can do on big blobs of text, for example. So there are some other techniques that we have for actually indexing data. And before I go into indexing data, let's talk about actually what indexing is. The most simple index you can think of is in the back of a book. I've got a picture of the Wikipedia book. So the index at the back of a book is essentially a list of terms sorted alphabetically with the number of the page where that term appears. So, for example, if I'm looking for the word zombie, I can actually, it's kind of optimized for that case because I can go to the back of the index since it's alphabetically sorted and then find my word there. And then I can go to my page and then I can scan that page and find the line where it is, and I can look in the line and I can find where the word zombie is. Now, if we want to make this index a little bit more complicated, and this is going to kind of hint to where these technologies really bring a lot of features, is what happens if I want to add things like, okay, let's have the page number on there, let's also have the line where that word appears, and let's also have like the offset into that line where that word appears so I can find exactly where that word is. Now that index isn't much more complicated, but let's think about other things. Like, what about synonyms? Like, what if I want to, if I want to find the word undead or something like that, I also want to see zombies in my result set. Or if I want to search ghouls, I also want to see zombies in my search result set. So maybe you can have different pointers. And you can see, like, you're already creating a more and more advanced index. Or what happens if you can't spell the word ghoul correctly? All these different things, you could put the different spellings of the word in there, you could put the different synonyms of the word. It becomes a very complicated index. And that's where Lucene comes in. So Lucene is an open source Apache project developed by Doug Cutting, and it creates a very complex index. We'll call it the Lucene index that allows you to do many different searches on it. And actually, different technologies like Solr and Elasticsearch, which I'll talk about, take advantage of Lucene to create that Lucene index. So when I talk about an index, I'm talking about kind of that back of the book custom Lucene structure that allows us to do complex queries on data that we've indexed. A lot of times I'll get the question of, when I'm indexing data in Lucene, what's actually in there? Well, it's that custom Lucene index. It's not necessarily the raw data. So if I've got a page in my Wikipedia book and I want to index that, in the back of the book, you're not going to find all the words like or the, because those have been omitted, so they've been used a lot. It's a unique data structure that represents a Lucene index that you can search on the data. It's not necessarily the data itself. So obviously, people are using Lucene to create their indexes, and they're also taking advantage of different technologies like MapReduce or Flume or Storm to parallelize their creation of this index. And there are some tricks to doing it, but the fact is that no longer do you have to wait a day to create your index on your data. You can parallelize it and get it done a lot faster. And sometimes, in the cases of things like Flume or Storm, you can get pretty close to real time. and here's the point where everyone says, well, what's real time? And that's going to differ for everybody out on the planet. Real time to some people might mean 5 to 10 minutes. Real time for other people might be 500 milliseconds. Real time for other people might be an entire day. Really, it depends. But depending on your architecture, you can actually achieve those different things, those different SLAs, I suppose I'll call them. Another definition of real time that you'll hear a lot if you're ever reading the Lucene or Solr or Elasticsearch documentation is the ability to search things before they hit disk. So now I'm getting a little bit more technical. So in Lucene, there's a feature where, well, I should say in the past, you had to kind of commit your index to local disk. So you had to write the actual Lucene index structure locally on disk. Well, there's a new feature that allows you to search that data before it even hits disk, so while it's still in memory. And that allows you to do very fast millisecond searches on your index before it's even written to disk. So the core message I want you to get from here is we know what an index is. It's a very complex structure, way more complex than that thing in the back of the book. We can parallelize it through technologies like MapReduce, Flume, or Storm, and you can search that index extremely quickly. So let's talk about searching that data. Not to say that you can't use Lucene to search your data. You can use Lucene. Lucene has tons of search features that you can use to search on that index. But they're all going to require you to use very complex APIs. So technologies like Elasticsearch and Solr build on top of Lucene to make it a lot easier to use and to add a bunch of new features on top of it. So essentially, Solr and Elasticsearch are search servers that are built on top of Lucene. So you can deploy these instead of your Tomcat or Jetty or whatever it is, and you can send RESTful queries that are easy to create to Solr and Elasticsearch, and they will interpret that, make the Lucene query on top of the Lucene index, and return back a nice JSON or XML response to you. They're extremely easy to bring up, and they add on top a bunch of different query features. So they've got every feature, for the most part, that Lucene has, and then they build on top of it. And so if you ever see things like Solr versus Elasticsearch, that's because they're pretty much main competitors in the space there. They offer a lot of the same features, but the underpinnings, the architectures are a bit different, and I'll get into that a little bit later. And they also have a few different features that set them apart as well. And again, I'll get to that later in the presentation. So let's talk about some of the basic search features that we want. Obviously, we want Boolean logic. We want sorting and group by. So if I search on like my favorite comic book artist, who is Tony Moore, I want to say I want to find everything by Tony Moore, and it has to be from The Walking Dead, and sort it from the newest comic book that he's drew, to the oldest one. These are different kind of basic search features that I want. You've got things like range queries. I could say I want it for the last month, or I want all the comic books that have costed between $10 and $20 or something like that. And then you've got kind of fuzzy queries. So that's kind of like your where-like in SQL. So you can say something like, if I want to find dachshund, but I don't know how to spell it, I can search on DACH star, or I can search things like D star HUNDS, and these will all bring back dachshunds. Those are kind of typical search features that everyone wants at a basic level. Some of the more advanced things are things like custom ranking and scoring. So by default, Lucene uses this TDIDF function, which essentially does it ranks different words in documents. So like I said earlier, the word "the" is obviously less important than a word like zombies if I'm searching on zombies. So the way that it's indexed is they take the number of times that that word appears in a given document, and it offsets that by the number of times that that word appears across all the documents. So obviously "the" is going to appear across many documents if you're talking about something like a text-based, I don't know, article repository. So it'll say "the" appears all the time in these other documents, so therefore if it appears in this document, it's probably not as important. But zombie only appears in 10 documents, and that's the word you're searching for, so that's obviously a more important word. And so in your result set, you'll get those more important documents first. And that's extremely customizable. You can go through there and you can say, well, I want this word to be ranked higher just because I've defined it so, or I want you to use this algorithm. Tons of different ranking abilities that you can put on top of your Lucene index. Then you got things like more like this. So if you're searching on a certain document and there are other documents that are very similar, can't think of an example off the top of my head. I suppose I'm searching for something like Lord of the Rings. I want to find all the Lord of the Rings things, and it can see that other documents are kind of related to the fantasy genre based on terms that appear in both documents, and it'll show me more documents that are like that. You've got auto-suggest, which is very similar to your Google, where you're typing in a word and it fills it out for you. You've got things like faceting or highlighting. Faceting is it's a way for users to discover data. It's essentially like on any kind of shopping site like Amazon, you'll get the counts of items. So if I'm searching for hard drives on Amazon or Newegg, it'll say, well, there's 15 external hard drives, there's 12 laptop hard drives, etc., and it'll give me the count, so I can kind of dig in there. Then maybe it'll give me the brand, etc. It's a way to help users discover data, and it's extremely powerful. Highlighting, I suppose maybe highlighting shouldn't be on the same bullet there. Highlighting is simply highlighting the terms that you've searched on in your query. And then you've got things like geospatial search, which is like when you're searching on Yelp or Google Maps, you can move around the map, which is essentially sending around coordinates, latitude and longitude, and saying search on anything within this latitude and longitude. So you can kind of project a map on your search index. And there are actually a lot of more advanced mathematical things that you can do with that geospatial search that don't necessarily have anything to do with maps, but I'm not going to get into that because that's pretty advanced stuff. But yeah, these are some of the cool advanced search features that you get with technologies like Elasticsearch and Solr. And of course, we're talking about big data, so these things better scale, right? And I put there cloud computing everywhere because it's such a cool word to use. But Elasticsearch was built to scale. That's one of the reasons that they started developing it, because they wanted it to scale. They were kind of making up for some of the features that Solr Cloud didn't have at the time. Solr Cloud is actually it's a set of features. You can call it Solr 4. Right now it's on Solr 4.3. You can call it Solr 4.3, or you can call it Solr Cloud. It's essentially referring to the set of features that allow you to easily create a distributed index. So they've got the auto sharding. You can say I want to split my index into 20 pieces, and it'll automatically set that up for you, and send the different documents to the right nodes and whatnot. It's got replication, so that if one of those nodes go down, you can get the index from another node, and it's smart enough to route the queries based on which nodes are down or which ones have heavy load. And then you've got a transaction log, so that if you're indexing a document on one of these nodes, it can pick up the documents that were supposed to be indexed from that transaction log. So it's got a great set of distributed features that is actually pretty easy to set up and start using right away. So now I've got a second poll. I'm going to go into the use case right after this one, so I know you guys are excited to hear about that. But I just want to learn a little bit more about you guys, and Anna's going to give you guys that poll.
Thanks, Ryan. The poll is, how far along is your organization in using big data technologies and techniques? We'll just take 30 seconds to let you guys answer this. So it's running the range of half of the folks are just starting, Ryan, and then the other half are pretty well experienced in at least one or two data projects, some being all about data.
Cool. Very cool. Then I think this should be interesting to most everyone. All right, so here's how I'm going to structure this. I'm going to go through the problem. I'm going to go through an example solution, talk about other technologies we could have used, and then talk about some of the problems we had. I'll actually swap those last two. So here's our problem. Remember, so we're talking about device data. So on the very left-hand side, we've got a number of different clients that have a number of different devices, and these devices are generating data and sending logs back to HBase. Sounds simple, but actually, in a big organization that has many different products and many different engineering teams, that can actually itself be a very tough problem. You'll find that while I've got a nice little box there that says HBase, that actually, is like a million different things. So product from 2010 is sending logs back on, via email to this server. Products from this year are sending it back to this file server through whatever protocol. You'll find that the data is kind of splattered all along, but we'll just call it HBase for now. And we'll just say that there's some process existing. So let me take a step back. So we're saying that this is the existing architecture for whatever company it is that has this data, device data problem. So this is existing. This is what we walk into. They're saying, hey, we need help because this isn't working. All right, so let's go back. So we talked about we've got different logs being sent back. They're making them back to HBase. And let's just say that there's some process that's dumping them into some, just kind of flat file, share that everyone can access. So if we've got, zips coming back from these devices, we've just got, some directories on a file share, and it's just the raw data as it came in, not touched, just simply dumped in this flat file area. And then I'm going to go through kind of the main flow first before I talk about the engineers and analysts down there. So then they've got some kind of ETL flow. So they've got some kind of scheduled parsing that happens on some basis that goes through these files. These parsers are very in tune with the data inside of these files. It's going through parsing out different objects like configuration, building some kind of entity relations inside of a relational database so that users down the line can do advanced queries based on that model. And this parsing job, as the data is getting larger and larger, this parsing job is taking longer and longer. So we've run into clients where for a given day, it takes a whole nother day just to parse and load that data. And really, that's unacceptable. So for, when I was talking earlier about, real-time response, if a customer has a broken drive or something like that, you want to be able to respond to that very quickly. A day is just completely unacceptable. So now we've got things loaded, and I put the latest there. So we've got the historical capture in that flat file, but in the Oracle database, since it's hard to scale, we can only capture the last week of data or something like that. And then from there, you've got some kind of nice services layer on top of your Oracle database, because this is what all of your applications, internal or external to customers, are using to access that data. So you've got different applications, like maybe a troubleshooting application that allows technical support engineers to search the log data for different things. Or you've got a user-facing application that says, here's the configuration of your different systems. All of these different applications, as I'm calling them, are using this services layer, I'm calling it the REST API, to do different queries on the Oracle database. And again, as the data gets larger, you'll even find that these queries themselves are taking longer and longer because the relational database just can't manage it. So that's another problem. So we got two problems so far. The first one is just parsing and loading the data is taking forever, and now searching the data through SQL is taking forever. The third problem is what we have at the bottom there, which is these engineers and analysts that are going directly to the logs, completely circumventing the process that we've developed in this SQL database. So we've got different product groups. A new feature comes out, and new data is coming back from the logs, and they're saying, well, I want to get that stuff right now, so I'm just going to go to the raw files and start parsing them myself. And you get 10, 12 different groups doing the same thing, starting up their own databases. You lose this central repository of data. Data is starting to get scattered. It might not be as clean. It might differ from group to group. Really what we want is one centralized location where users can perform queries together. So everything is centralized. So that's our third problem, centralizing our data. All right, so now let's talk about some of the different queries that this REST API should serve. So to get to the point here, what's going to happen is we're going to replace that Oracle database. We're going to replace some of that Oracle, we're going to replace that Oracle database and some of that ingestion flow with different pieces of the Hadoop ecosystem. So the one thing that's really facing our customers in this case, or our applications, is that services layer, that REST API. So we want to maintain that same search service layer on top of this new architecture as we do on this current architecture. And here are some of the features. And I already kind of alluded to some of these. So a technical support engineer might say, I want to find the last 3 days of raw logs from a cluster. A client has called in. They said that for the past 3 days, they've had terrible performance. I just want to go to the straight logs, and I want to see them. So we still need to maintain some kind of raw access to that data. Another different use case could be, I want to group the capacity available. So if we're talking about hard drives, I want to see how much percentage across my entire cluster am I using. So let's group them by the machine serial number and show the ones that are the most full first. Or another technical support kind of use case, just I want to do a full text search. I want to find the word failure in any of these logs, and et cetera, et cetera. View all hard disk objects that have a certain product number. Or, this is a cool one too, find all the motherboards that are associated with a customer ticket. So someone may be trying to do some preventative action there, finding the different models of devices that are causing problems with other clients, and then maybe warning people and saying, hey, we've seen a lot of problems with this. So it's just a small subset of queries that people tend to want to do on their data. So here's our sample solution, and this is fairly high level still. After I go through talking about this overview, I'm going to go through each piece there, so ingestion, parsing, loading, indexing, etc. So at the top, we've got the logs, and like I mentioned, these logs come in, they come to home base, but even at home base, they're still kind of littered all over the place. So the technology that we're going to choose here is Flume, and Flume is really good for taking data from many, many different sources and then bringing them down into one spot, in our case, HDFS. Flume is actually developed to kind of suck in log files that are scattered about a cluster and bring them into one place. But here we're just going to tap onto all the different sources that we have, and then as those new files are coming in, suck them into HDFS. So now we've got our raw files in HDFS, and now we're able to use MapReduce on top of HDFS. So we're going to use MapReduce to do that indexing. As you see, it's got that arrow down to Solr. And we're going to also use it to parse and load HBase with those kind of parsed objects that we were doing with our ETL before. So we're going to load big chunks of the data, big parsed objects, or it doesn't necessarily have to be parsed. They can be whatever you want. You could throw that into HBase. But anything that goes into HBase, the core requirement is we want to access that data quickly and kind of randomly. So we're parsing, loading HBase, we're indexing Solr, and then on top of that, we're going to keep that same search layer that uses Solr for the index, that tells us where different terms are appearing. We're going to store some of that data inside of HBase for kind of real-time random access, fast access. And the last thing is we're also going to have that ability to go back to HDFS and bring back the raw file if the user wants that. So let's dive into each of these pieces individually. And I'm going to get a little bit technical here, so I hope this doesn't throw too many of you off. One of the big problems that you'll have with Hadoop, it's funny I call it a big problem, it's called the small files problem. So these different pieces of device data that are coming back, product logs that are coming back, they're not necessarily large. You know, it's one of the clients that we worked on, the logs were somewhere between like 1 megabyte and like 10 megabytes. You know, even some of them are smaller in kilobytes range, with maybe a few outliers that are huge. So what we're doing here on the left, so let's say that a product log is defined by color. So here we've got 4 different product logs, a green one, a pink one, a yellow one, and a blue one. And these product logs actually come in as like zip archives. So we see there's 4 files in the green one, there are 4 files in the pink one, 2 in the yellow, and 3 in the blue. What we're going to do to kind of avoid this small file problem, let me back up and just explain the small file problem. Again, Hadoop is really designed for kind of large sequential reading. So you want to get big files in there so you can do those big sequential reads and not kind of seek your disk head to different spots. Again, this is very technical. Just know that Hadoop really likes big files. So we're going to use these things called sequence files, which allow us to deposit smaller files into a larger container inside of HDFS. So as you can see there, Flume is taking these different things, these different product logs, sucking them in and kind of depositing them into these containers here. We've got 1, 2, 3 containers. Those are sequence files. And it's dumping those individual files from the product logs into those sequence files to a file size that makes sense for Hadoop. So 4 of the green files and 1 of the pink, that makes up the right file size. Let's continue. Let's make a new sequence file. Let's dump the rest of the pink in that one, and then merge the blue and the yellow together. So now we've got 3 sequence files of an ideal size sitting inside of HDFS waiting for us to do some analysis on it. And the beauty about Flume is that a lot of this stuff is built in. It's, you know, they've got the sequence file support. They've got a bunch of different features that allow you to discover new data as it's dropped onto a directory, etc. If you guys ever use Flume, it's a great technology to suck in data from many different sources, get it into one spot, and even do some transformations on that data. In this case, grouping them in sequence files, all pretty much built in. So that's Flume for you. The next piece is parsing and loading and indexing. So again, we're looking at the 3 sequence files here that contain the product logs coming from 4 different machines: the green machine, the pink machine, the blue machine, and the yellow machine. And as we deposit these files, so I mentioned before that we're defining a product log as like a zip file, and the zip file contains many different files in it. For the green one, the zip file contains 4 files. For the pink product log, we've got 4 files inside of our zip. So as we're depositing these files inside of the sequence files, we can actually take note and capture some metadata about where we put that. So we can say, I put the first file for the green product log inside of the first sequence file, ingestion sequence file 1, and that first file is found at the 0th byte in that sequence file. The second file came in at 1534 bytes inside of that sequence file. So there's actually really easy to use APIs that, as long as you have that file path and that offset, you can immediately look up any of those files that came in. So if a user says, I want to get the third file from the pink product log, we can say, okay, well, that's in ingestion sequence file 2 at byte offset 4601, and that API will bring us back that file from the sequence file. So you can already see we're already starting to talk about that use case where people want to see the raw archives. So when we run our MapReduce over this raw ingested data and we're doing our parsing and loading it with HBase, we're also going to store those file paths and those file offsets in the sequence files inside of Solr. So just like in the back of the book where we say, I want to see where the word zombie is and it's got the page number, we'll say, Solr, I want to see all the things that have the word failure in it, and it'll give us back the sequence file path and the file offset so we can immediately look up that file. And this is really just a simple secondary index. And then also, so remember, we're doing that parsing of the objects inside of HBase. And I mentioned before that inside of HBase, you can look up records given the row key. So we're also going to store that in Solr. So we can say, find me, all of the motherboards that have this case ID, and then it'll also bring back that row ID along with the HBase row key along with the sequence file path and sequence file offset. So that's our parsing, loading, and indexing bit. And this is just an extremely crude example of what's inside of HBase. Really, what I just want to show here is that there's a bunch of data inside of HBase, and then we've got these different row keys defined by the different product logs. So maybe for the yellow product log, some of these objects, whatever, they might be like the motherboard configuration, the enclosure type, whatever it is. The idea is that you can go back with that row key and find that data quickly. And then we've got the Solr document. And like I said, the index is like the back of the book. Here we're modeling it in terms of documents. So in the back of the book, we've got terms with numbers next to it. Here we've got Solr documents that contain fields. So for example, with this Solr document, I could search on, show me all of the logs from 2013-05-12, and I'll get back this information in my query. I'll get back, remember, we've got that sequence file offset, that sequence file path, and then we've got that row key that I'm showing as color here, since I showed the row key as a color in the HBase schema. So you can start to see, this search service is going to have a flow, right? The first thing it's going to do is it's going to query the Solr document. The Solr document is going to give us back some information that we can use to query other things as well. And that's where this picture comes in. So here we've got the flow from 1 to 8. The user makes a query. It's got that services layer, so we're going to do some interpretation into a Solr syntax, and that's step 2 there. We're going to make our query to Solr. Solr is going to give us back that information in the Solr document. And even at this point, the Solr document has a lot of information here. If we just want to search for all of the systems that have the word warning in it, Solr, we chose to index some other metadata and store some other metadata in Solr. So even at this point, we can give back a list of system IDs that have that header. That's just one quick call. Now, if they want to get additional, configuration data that, is stored inside of HBase, we can use that row ID, bring that back to the search application, and give that to the client. Or if we can make a third step and go to HDFS with that sequence file path and offset, gather the actual raw file itself, and then give it back to the client. So, the API is going to have many different services. Some of them are only going to use Solr. Some of them are only going to use Solr and HBase. Some of them might use Solr and HDFS. It's really a kind of mix match based on what APIs you want to use. And so here are some of the common issues that we ran into with Solr. So one of the things about Solr is that when you're defining your index, the way that you want to index data, you define the schema. And that basically tells Lucene how you want to index the data. So for example, if we want to index a whole page of text, let's say we want to tokenize by like white space. And that basically means that every token you can search on that token. And we want to search on tokens defined by white space. And that's how you index your data for the past year. Well, if tomorrow you decide that, oh, well, I actually want to tokenize on white spaces and hyphens, well, that's going to completely change your index. So you have to go in there and you have to manually redo that, re-index all of your data if you're changing the schema. And that goes for many other different things. You know, you can define things like data types, different fields. Solr and Elasticsearch have very flexible schemas, but there are certain things that you want to act a certain way, and if you ever change them, you have to manually reindex them. So that's definitely a big problem there. And then what I call elastic shard scaling. So Elasticsearch and Solr both give you the feature to say, I want to start a 30-node cluster, and I want to spread my index across those 30 nodes. Well, that's great, and hopefully you've done some planning to say that I know that in the next year or 2 years, my cluster will not grow past 30 nodes because I won't have that much data. But eventually down the line, you'll find that, hey, I need to add some more nodes to this. And if you want to do that, you have to manually reindex, essentially redistribute the load across the 40 nodes. So that again, this manual reindexing process is not only going to take a lot of time, depending on what size of the data you have, but it's also going to require some developer effort to kind of do a re-indexing, going back over the raw data and then parsing out the index and depositing that to Solr. So that's definitely a big problem there. The other problem is that there really isn't any support for distributed joining. I've heard Elasticsearch has some unique features that you can use to kind of simulate joining in a distributed environment, but really at the end of the day, that's not the kind of query you want to do. So you'll really want to spend some time denormalizing your data, and that just means flattening it out. So instead of having many different relations in a table, or in a set of tables, you want to have one flat schema for your data. And then we've got a few different other things like replication and Solr partitioning and sharding and write durability. A lot of these projects that I've worked on have been, I've been working in this field for a couple of years now, and so we're using older versions of Solr, which didn't have Solr Cloud. And I'm going to talk a little bit more about Solr a little bit later, but basically that meant we had to use the older Solr versions which didn't have these features. So I don't really count those ones as much, since now we've got a lot more different kind of features and different products we can look at to solve these problems. So let's talk about Solr Cloud for a quick minute here. Again, Solr Cloud is a set of features that were introduced in the Solr 4.0 release. Right now, Solr's at version 4.3. Solr in general has been around for a very long time, but it wasn't until I think it was like October or November of last year that these Solr Cloud features were implemented. So, and they're actually changing quite a bit still to this day. So I wouldn't necessarily say that the distributed features are necessarily fully mature yet. Definitely a lot of people are using them, but you'll still find yourself running into a bunch of problems if you're going to be using this in the production. So it's got automatic shard creation, routing, replication, all those things that we talked about earlier in the presentation. And again, you're limited to that number of shards as I just described. If you want to add more shards, you have to completely reindex manually. It uses Zookeeper, so if you're familiar with Hadoop, you know that Zookeeper is a big player in that ecosystem for kind of managing where shards are and what their configurations contain, etc., like that. So Solr takes advantage of that when it's creating a distributed index to know different things like the schema for the index, etc. So Zookeeper will maintain that those configurations in different states about the cluster. And Solr has a huge community, definitely the largest. Lots of support online. The mailing list is just always going. So it's definitely a great place to look if you're looking for search. And like I said earlier, there's also Elasticsearch, which essentially has a pretty much the same feature set as Solr. Like I said before, there's a couple small features that are different, but really they're pretty much toe to toe at this point. But the one unique thing about Elasticsearch is that it was built to make up for all of those shortcomings that Solr had, prior to Solr Cloud 4.0 release. So when Elasticsearch was built to kind of make distributing an index much easier than it was pre-Solr Cloud. So it's you don't have to set up Zookeeper. It's got its own kind of coordination technology. It's called Zen something. Sorry, I'm forgetting the name for some reason. So it's all built in. You don't have to set up a separate Zookeeper cluster. It's all built into Elasticsearch, pretty much transparent to the user. So it's really easy to use. It also has a JSON-based API. You can use JSON with Solr as well, but yeah, the Elasticsearch is strongly focused on that JSON API. And yeah, in the community there, it's grown significantly over the past year or so, but I wouldn't say it's quite as large as the Solr community. The next thing that you can take a look at is DataStax Enterprise. So DataStax will actually kind of merge your NoSQL database and search together. So it uses Cassandra as its NoSQL data store and uses Solr to search. So if you, we talked a little bit before about how we were going to use MapReduce to parse and then load HBase with these complex objects, and then we're also going to create the index on our own. Well, with DataStax, you can simply submit a record to Cassandra, and it'll automatically be indexed inside of Solr. Or you can index a document inside of Solr, and it'll automatically store all of the raw data inside of Cassandra. So, and it also pairs the partitioning mechanisms of Cassandra and Solr together. So when we talked about before, where you have this fixed number of shards, with Cassandra, that's not, with DataStax, that's not the case. DataStax will manage the sharding of Solr internally. You don't even have to care about it. It basically piggybacks on top of Cassandra's partitioning strategy, and it'll automatically do the reindexing for you. So you've got that elastic sharding capability. You can also use that automatic reindexing for things like schema changes, etc. So it's a really beautiful technology. It's been around for a while now, but the thing is it costs money. So that's kind of an issue for a lot of people, and it's proprietary, so you can't dig into all that code. But if you've got the money to spend on it, it's a great thing to use. I've used it before, and it just works. It's great. And recently, I think it was sometime last week, Cloudera announced that they now have a search offering, which is kind of a parallel to what DataStax has on top of Cassandra. So Cloudera has now merged Solr with HBase, and so it's got that partitioning from HBase. It's piggybacking on top of that, and so you've got things like reindexing, search on top of your data that's inside of HBase, etc. And MapR also has something similar. They made an announcement sometime back in April. I haven't heard much of it since, so I'm not really sure on how far along that is. But I know with Cloudera, you can actually download and start playing with that stuff today. Some of the other cool stuff that Cloudera has, they have a Flume Solr sync. So back in our architecture, we talked about Flume looking for new data and just depositing it inside of HDFS. Well, that's using a thing called an HDFS sync. Looks like now we've got this Flume Solr sync. So if you want to have kind of automatic index, or I shouldn't say automatic. If you want to have fast indexing based on your ingestion rate, you can just plug in that Solr sync, and it'll automatically index your data that's going through Flume, and that's really cool. And in addition, if you guys know anything about Avro, it's a serialization technology with a flexible schema. It'll actually use that Avro schema to apply that to different data types in Solr automatically. So there's a lot of really cool stuff in here. The architecture that I showed you was kind of the manual way to do what they're doing here. So allowing you to search on data inside of HDFS, allowing you to search on data inside of HBase. I haven't dug into the source code myself yet since it was only released last week. Well, actually, sorry, I can't even dig into the source code. I haven't looked at the source code, so I don't necessarily know exactly how it's working, but I'm sure it's something similar to what we outlined before in that architecture. So I hope you guys all learned something today. Search is really cool. Everyone wants it. It's definitely not the easiest thing, but hopefully this gave you guys kind of a high-level understanding of how search comes into play with these big data NoSQL ecosystems. And yeah, so you can either do it the hard way, do it yourself, or you can look at those proprietary solutions that I just talked about. And if you guys have any questions, here's how you can contact me. ThinkBig is going to have this presentation on their website, so if you want to look at it or rewatch this webinar, you can go to ThinkBig's website. Feel free to Twitter me, whatever it is. I'd love to answer your search questions. So, and if there are any questions now, I know we've only got a couple of more minutes, but I'd be willing to take any questions from the crowd.
Ryan, we're actually running at an hour, so I do encourage you to email your questions to Ryan at ryan.tabora@thinkbiganalytics.com, or you could tweet him at Ryan Tabora. Actually, we have time for one question. Ryan, they were asking if you could go back to that architecture slide or the search application slide.
Okay.
And just quickly walk through that again.
Sure. Yeah. So, and again, this is kind of what we were talking about with how Cloudera or MapR is probably doing this. The user comes in with a query, whatever it is. With Solr, the interface is kind of like an HTTP REST type style query, so it's going to be like kind of key values delimited by slashes or whatever it is. That's going to be a very company unique type query. Our search application is going to go through, parse that into the Solr query syntax, which is pretty similar, but you kind of want to have that layer there to put a layer between the users and the actual technology before it, so that if you ever swap out the technology underneath it, you can still maintain that search contract. So inside our search application, we're going to translate that into a Solr style query, get back what we have inside of that Solr document, which could be the sequence file, offset, whatever it is, and we're going to use this data in here, kind of like the numbers in our index, as a way to look up data inside of HBase or HDFS. So I'll leave this up here if you guys want to study it, take a screenshot, whatever it is. Like I said, it'll be available for you guys to look at later, but yeah, hopefully that helped.
Great. Thank you, everyone, for joining us. And again, the presentation will be available on our website later today. And if you have any questions, please feel free to email Ryan. Thanks for joining us.
Awesome. Take care, guys.